So I'm going to have 1 divided by 1, which would be a plus minus 1. 1 divided by 2 would be a plus minus 1/2. And then I have to continue on. 2 divided by 1, we have plus minus 2. 2 divided by 2 is plus minus 1. I don't need to rewrite that again. So it's just plus minus 2 there. And then plus minus 3 divided by 1. So plus minus 3 divided by 1, which would be plus minus 3. And then plus minus 3/2. And then plus minus 6 divided by 1 would be plus minus 6. And then plus minus 6 divided by 2 would get us 3 again, so we don't have to write that one. So these are all my possible zeros, but I want to identify which one is actually a 0. So let's test them out. So if I tested 1, P of 1, if I put this in, I end up with negative 10. That doesn't help me out. So I go on my progression. I'll try P of negative 1. When I do this, I do get 0. That's what I want to happen. So this tells me that negative 1 is a 0. And x plus 1 is a factor. So that's telling me a lot of information. So negative 1 is a 0. X plus 1 is a factor. So I'm going to use synthetic division to come up with the other factor. So it's going to be negative 1, 2, 1, negative 7, negative 6. All right, pay close attention on this because I think there's still a number of us that aren't comfortable with synthetic division. So the first thing is we're going to bring the 2 down. So 2 comes down there. Times negative 1 is negative 2. Add those together. So 1 plus a negative 2 is negative 1. Multiply negative 1 times negative 1 ends up being positive 1. Negative 7 plus 1 is a negative 6. Negative 6 times negative 1 is a positive 6, which gets us 0, which is what we want to happen. So this tells us that we've done our synthetic division correctly because we knew it had to be 0 with a remainder. And now I can build this. So this is 2x squared minus 1x minus 6 is my other factor. So I know x plus 1 is a factor, and I know 2x minus 1x minus 6 is another factor. Let's factor that one down a little bit further, though. So 2x squared minus x minus 6. So 2 numbers multiply to get negative 12 that add up to be a negative 1. I'm going to get negative 12. I could use a combination of 2 and 6, 4 and 3. So if I do a negative 4, positive 3, that'll work. But because I have a coefficient of 2, I have to do that 4 spots where I break up that middle term. So this becomes 2x squared minus 4x plus 3x minus 6. And I want to do my factor by grouping with these. So in this one, I can factor out 2x, and so it becomes x minus 2. This one also has to be x minus 2. Factored out a 3, and it's positive 3. So I end up with 2x plus 3, x minus 2 as my factored form. So putting this all together, I know x plus 1 is a factor. I know 2x plus 3 and x minus 2. That is the same as my polynomial p of x. This tells me that x equaling 1 is a solution. X equaling a negative 3/2 is a solution. And x equaling 2 is a solution. So those are my 3 zeros that I'm working with. All right. Okay, I can't hear you very good. No. Okay. It should still work out. Yep. So which other one did you get? Which other one did you choose? So, okay, so you would have used 2 in your synthetic division. Okay, your polynomial might have been different. Okay, but still you should have ended up with the same x values in the final answer. You're saying you did not? Okay, I'll look at it with you. Okay, but yeah, it should still work. So essentially, you just started with identifying that 2 was a factor, and then you could do your synthetic division and get the other ones. All right, so here was a crash course on everything we did yesterday, and this was a lot. Today's going to be a lot. Okay, so you need to be fully attentive, ready to go, because today's another one that you have to pay attention on, work through it, fill in your notes. The actual math I don't feel is hard, but it's keeping organized, following the process that's the hardest part. If you stay organized, you follow the process, it works out every time. All right, so this is, you don't have to write this down. So yesterday we did what's called the rational roots theorem, which again, this is with integer coefficients. Okay, you can't write it with decimals, can't write it with fractions. These are integers. Integer roots must be plus minus factors of the constants, and then the rational roots will be plus minus factors of the constant divided by factors of the leading coefficients. All right, this is everything we did yesterday. Before we get into today, let's just do a quick recap from concept 8 when we talked about complex conjugates. If we had a division with that imaginary unit I, we had to multiply by the complex conjugate of the denominator. So if we were dividing by 1 plus I, we would multiply by 1 minus I all over 1 minus I. That's how we would do it. That's what we did in concept 8. That 1 minus I is a complex conjugate, but this idea of conjugates we're going to work on even more today. So a complex conjugate, dealing with complex numbers, is a plus bi and a minus bi. Okay, all we did was switch that sign in between the a and b. We can also do this with irrational numbers. And we can have conjugates with irrational numbers, and this is what happened in problem number 1 from last night's homework. We ended up with 2 plus root 3 and 2 minus root 3. All right, so we have conjugates with irrational numbers as well. Simply, the only difference is the sign in between each piece. Okay, so we have a new theorem to go along, which is called the conjugate root theorem, and this is for rationals. If p of x is a polynomial with rational coefficients, so our coefficients on our variables, we can write as a rational number 1/4, 3/8, whatever. Then the irrational roots are going to occur whenever our polynomial is equal to 0. They will take on the form of a plus root b, and they're going to occur in conjugate pairs. Meaning, if we identify that we have a root that's a plus root b, then a minus root b is also going to be a root. It's going to be a 0 of our function. Okay, so what this theorem is telling me, if I have one, I automatically know I have the second one. They come in pairs. Okay, so that's the biggest thing you need to pull from this conjugate root theorem, is if you get a conjugate root, so a plus root b, then a minus root b is also going to be a root, which is a 0 of the function. Okay. We also have a conjugate root theorem with real coefficients. So if we have a polynomial with real coefficients, then the complex roots, where a polynomial is equal to 0, occur in conjugate pairs. That is, if a plus bi is a complex root, then a minus bi is also 1. So what we can do, if we recognize that there's 1, the second one is with it, even if it's not written. Okay, we can automatically say, yep, if it's a plus bi, it has to be a minus bi, so there's 2 of my roots. Okay, so the big thing about these two theorems is, again, they're just telling us that they come in pairs. If we see one, the other one is automatically there. Okay, we can immediately just write it down because it has to be there as well. That's another 0. Okay, so we have an example here of a quartic polynomial p of x. What's quartic mean? What degree would that be? 4. So degree 4 polynomial is a quartic, so I know there's going to be 4 zeros. Okay, and it could be a mixture of real and imaginary zeros, but I know there's going to be 4 zeros. Has rational coefficients. If they tell me square root of 2 and 1 plus I are roots, that's where my polynomial equals 0, what are the other ones? Well, my theorems tell me then that if I know one of them is square root of 2, so that's really 0 plus square root of 2, well, then I can already say that 0 minus square root of 2 also has to be a root. And if they tell me 1 plus I is a root, my theorem tells me that 1 minus I would also have to be a root. So these are my 4 roots. With them only telling me 2 of them, I already know what the other 2 are based on those 2 theorems. And so I would just simply list them out. I could say plus minus root 2, and then 1 plus or minus I. I could list them all out that way. And that covers all 4. Okay, let's actually start doing one. Write a polynomial function with rational coefficients so that p of x equals 0 has roots at 7 and 12. So again, roots, all the roots mean are the zeros. So we've actually had a test question that asks pretty much the same thing. If I tell you the zeros, what's the polynomial function going to be? All right, so if my polynomial function p of x, if a 0 is at 7, what am I going to write in my binomial? So if I know 7 is a root, it's going to be what? All right, what do you say? No, correct. It's going to be x minus 7, because that, if I put 7 in there, it gets me 0, which is what I want. And then this would be x minus 12. What I want to emphasize here is it's x minus every single time. Even if if they gave me a different problem and said the root was -7, I want you to be in the habit of writing it as x minus -7, which you could simplify and say x plus 7. But I want it in your brain every single time. If you're told the roots, you write it as x minus whatever they told you. All right, but we want a polynomial function with rational coefficients, so let's work this out. So we can work this out with FOIL. So x times x is x squared. X times a -12 would be a -12x minus 7x. And then 7 times 12 gets me a positive 84. I would combine like terms. X squared is going to be a -19x plus 84. So if they told me the roots, I can immediately say, okay, those are my roots. I can write it as x minus 7 and x minus 12. I can FOIL. This is the polynomial that has those two roots. So we're in a sense working the other direction now. We're building the polynomial by knowing the roots. All the other problems we've been asked, okay, tell me the roots given this polynomial. Simple enough. Okay, let's turn the dial up a little bit then. Same thing, write a polynomial function with rational coefficients where p of x equals 0 has roots 13i and 5 plus 10i. All right, and so this is going to be my polynomial function. So if 13i is a root, what am I going to write in my binomial? A minute ago we did it with 7. What happens now if it's 13i? What am I going to write in my polynomial? So x minus 13i. But 13i, I know there's also another root. If they told me 13i is a root, my theorem tells me what else is going to be a root. X minus what? Nope, not that one yet. So if 13i is a root, what's another one? Don't even look at the 5 plus 10i yet. Okay, so it's going to be, well, it's going to be the opposite. So it'd be a negative 13i, but still, yes. So I can immediately say if I know positive 13i is a root, negative 13i is also a root. Okay? If they told me that 5 plus 10i is a root, I'm going to say x minus, and use parentheses here. So 5 plus 10i is a root. And then I'm also going to have x minus 5 minus 10i as my other root. So if it's a positive 13i, my theorem tells me negative 13i is also a root. If it's 5 plus 10i, my theorem tells me that 5 minus 10i is also a root. Okay? Everybody comfortable with that? Again, start out with subtraction every single time. So this is x minus 13i, x plus 13i. I can simplify it to look like that. Now I need to multiply these together. So let's do a quick separation here. Let's not even worry about that 5 plus 10i and the 5 minus 10i piece. Let's just look at this x minus 13i, x plus 13i. To work this out, we need a FOIL. Oops. Come on. There we go. So in order to FOIL this, I'm going to take the first term. So it's x squared plus 13ix minus 13ix. Negative 13 times a positive 13 would be a negative 169 I squared. Emma.
I thought that an I would be
So I is on itself. I squared is negative 1.
Yeah.
So this right here, this I squared is really negative 169 times a negative 1. So it's going to be a positive 169. This one that I got here was x times 13i, and then this x times this 13i. So there's no I squared going on in these middle terms. Yep. But one thing we should recognize, 13ix minus 13ix, those are going to go to 0. I don't have to worry about those. Okay? And then we already did this, but here on the right, negative 169i squared. I squared is really negative 1. So it's negative 169 times negative 1. It's become a positive 169. And so this is x squared plus 169. But again, this is only the first two binomials of my entire polynomial. We have to do the piece on the right as well. Okay, so let's look at that piece on the right. We had x minus 5 plus 10i, and we have x minus 5 minus 10i. So this is still, there's still 4 terms going on here. So we can still FOIL. There's one here, there's one here, there's one here, and there's one here. We're going to treat that 5 plus 10i as one thing. Okay, so we can still use FOIL. First, outside, inside, last. So my first term is going to be x times x, which is x squared. And then x times negative 5 minus 10i would be a negative x, and I'm just going to leave it outside the parentheses. So negative x times 5 minus 10i. Inside terms is going to be another x, because this negative sign right here. So negative x 5 plus 10i. And then last, we have a negative times a negative, so that'd be positive. And it's 5 plus 10i times 5 minus 10i. So let's work on simplifying a little bit. We've done all our foiling. So if I distribute this x into each term, it'd be a negative 5x plus 10ix minus 5x minus 10ix. And then here at the end, we have to FOIL again, because we have 5 plus 10i times 5 minus 10i. So if I FOIL this, 5 times 5 is 25, and then be a negative 50i, positive 50i, and then minus 100i squared. Getting long, aren't they? Okay, use plenty of notebook paper, stay organized. And this is only the second half of the problem. Remember, we still have that last slide that we're going to have to bring back in a minute. Once I have everything multiplied through here, let's look at what we can eliminate. All right, I have a positive 10ix and a negative 10ix, so those are opposites, so those go away. I have negative 50i, positive 50i, those go away, I don't have to worry about that. So I can start building this up. This becomes x squared. Negative 5x is a negative 10x. Negative 100i squared is negative 100 times negative 1. So this becomes a positive 100. I still have this 25, so 25 plus 100 is 125. All right, so this set of binomials multiplied together is x squared minus 10x plus 125. But we also had this one here, x squared plus 169. That was everything left of my dark line there. So all four of these are multiplied together. So this one is going to be multiplied together with this one. We're not done yet. We have to multiply these together still. Okay, so this one we need to work on. Let's multiply x squared by each term on the right. So I'm going to take x squared and multiply it here, x squared and multiply it here, x squared and multiply it here. And so I'm going to have x to the fourth minus 10x cubed plus 125 x squared. And then I have to take 169 times each term. And so I'm going to have plus 169 x squared. And then minus 1,690 x. And then the last one, 169 times 125 ends up being a positive 21,125. Only thing I can combine, these both are x squareds. So I can combine those together. So I end up with my final answer. My polynomial in standard form is x to the fourth minus 10x cubed. When I combine these together, I get positive 294 x squared minus 1690x plus 21,125. That is my final answer. That's the polynomial that when I find the zeros of it will be 13i, negative 13i, 5 plus 10i, 5 minus 10i. One problem. It's a lot. Stay organized, okay? Don't be afraid to use too much notebook paper. Make sure you're following through on the process, because the biggest thing to recognize is at the very start, writing these every single time as x minus your roots. So x minus, and then it's just FOIL from there. But staying organized as you work through the problems. I did one more. This is on the notes in the slides that are in Schoology. I won't work through this whole problem. If you want to look through this one on Schoology, the notes have this one worked out. But I want to allow you time to get started here in class to work on the assignment and ask me questions if you have questions. Okay? And what I didn't do, you can look back in Schoology and see how that one works out. You can work it out as practice.